We're at lesson 14.5 and we're going to be proving mathematical statements. This is mathematical induction. If you haven't seen the previous 13 videos and you start to become lost or confused, it's a good idea to go back and check this description and find out what you're missing and catch up again, okay? So using the principle of mathematical induction, we can prove that statements about positive integers are true. This is the principle of mathematical induction. It says if P sub n is a statement concerning the positive integers n and P sub 1 is true for n equals 1 and assuming P sub k is true implies P sub k plus 1 is true, then P sub n must be true for all positive integers n. Now, if you're really confused, stick with me, okay? To prove a statement false, all we need is a counterexample, but proving a statement true needs a more formal method. That's why we use this, okay? So first let's get this out of the way. A conjecture is an opinion or conclusion that's made on the basis of incomplete information. So let's say Bob gives me $1 on Monday, $2 on Tuesday, $3 on Wednesday. We can make a conjecture that he'll give me $1 more each day and how much I'll have on a certain day. But a conjecture is incomplete information. We're just kind of guessing that that's what's going to happen. Well, for the principle of mathematical induction, we can prove a conjecture is true if we can show that something works for the first case, that's the base or anchor step, and if we can assume it works for any particular case, that's an inductive hypothesis, and if we can then show it works for the next case, the inductive step. So here's what I want you to do. I want you to imagine a staircase with an infinite number of steps. It's starting on the ground and it's going all the way up into the clouds forever and ever and ever. All right? That very first step is the anchor step. And then going up the stairs one step after another, the random one in the middle would be the inductive hypothesis. And then we've got the inductive step. That is one more than the inductive hypothesis. See that? So we can pick some number step like, 23 or something, and then add 1 to it to get the 24th step. See what I'm saying? Okay? So some of you are going to get what I'm explaining in the next few minutes. Some of you aren't. If you don't get it, still stick with me, okay? We can use the principle of mathematical induction to prove that the sum of the first n even positive integers is n squared plus n. So we're going to prove that here remember, it says even positive integers, so we've got 2, 4, 6, 8, 10, 12, blah, blah, blah. So we're going to prove that 2 plus 4 plus 6 plus so on plus 2n is equal to n squared plus n is true for all positive integers n. So here's our conjecture. We're going to let P sub n be that statement, okay, that we're trying to prove is true, all right? Our anchor step, we're going to make sure P sub n is true for n equals 1. That's the anchor step, that n equals 1, okay? So here we have P sub n, and this is what we're trying to prove is true, all right? Same thing. P sub 1 would then be 2 equals 1 squared, because it's 2 times 1, all right, which is a 2. It equals 1 squared plus 1, and 1 squared is 1 plus 1 is 2, so yeah, it's true. P sub n is true for n equals 1. Now, the inductive hypothesis, that's that random middle number we're going to try to use as k. We're going to assume that P sub n is true for n equals k. We can write this by replacing the n with the k in P sub n. So, everywhere that we had the n is now going to be a k. So it's going to be 2k equals k squared plus k. See? We're going to assume that this is true. So this is our inductive hypothesis, okay, with the k's in place of the n, all right? Now, here's the inductive step. We're going to use that inductive hypothesis where we put the k's in place of the n to prove that P sub n is true for n equals k plus 1. And to prove this, we need to show that P sub k plus 1 must be true. So we start with our inductive hypothesis where we replace the n with the k's, and we add the next term. That would be the k plus 1th term to each side. Okay, so here's our inductive hypothesis. Here we add that k plus 1th term to each side. Okay, so now we've added it to each side of the equal sign. When we simplify the right side, we get k squared plus k plus 2k plus 2. Because of distributive property, we get 2k plus 2. See? We simplify this right side, this 2 can be a 1 plus 1. When we factor this, we get the square of k plus 1 and plus k plus 1, see? Our final statement is exactly the statement for p sub k plus 1, so it's true. If p sub n is true for n equals k, then p sub n is also true for n equals k plus 1. So that means it's true for n equals 2, n equals 3, and so on. So by the principle of mathematical induction, p sub n is true for all positive integers n. Okay? Now, if you're still confused and you're going crazy, stick with me, okay? If in this inductive step we get a contradiction, then our assumption might be false, okay? All right, so let's try it again. We're going to try it again, and then it's going to get even easier over here, okay? So stay with me. We're going to prove that 1 plus 2 plus 4 plus 8 plus so on plus 2 to the nth minus 1 is equal to 2 to the n minus 1. We're going to show it's true for n equals 1. So we're going to put a 1 in the place for n. All right? So now we have 2 to the first power minus 1. That means we're going to have 2 to the 0 power, isn't it? And remember that anything to the 0 power is a 1, so that's 1 equals 1. So yes, it's true. So suppose the statement is true when n is equal to some integer k. All right? So we could pick some random integer and put it in the place there. So now we're going to put k in place of where n was, all right? Is the statement true when n is equal to k plus 1? So adding the k plus 1th term to each side of the equation should give us 2 to the kth minus 1 minus 1, okay? We add it to both sides of the equal sign, and we get 2 to the kth minus 1 plus 2 to the k. We can regroup and factor, and when all is said and done, we find out that it's true, okay? If you're still lost, this should clear everything up, all right? So remember we were talking about Bob? So I want you to think of it as Bob gave me $1 on Monday, $2 on Tuesday, $3 on Wednesday, and so on. You don't need any of this to figure out how much he gave me by Saturday or Sunday, do you? We could just add it up. Monday would be our a sub 1. Tuesday would be our a sub 2, and so on. We could just add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, total it, and know what he gave me, right? If we did that, he would have given me $28. For the next day, I'd be at $36 because we would add 8, right? Okay, so try to follow me on this, thinking of it this way, all right? And this way. That means we have 1 plus 2 plus 3 plus so on plus n. And that would mean that we have the quotient of n times n plus 1 to n2, see? So if we're doing the 7th day, that would be Sunday. We put a 7 here and a 7 here. That means we have 7 times 8, don't we? That's 56 divided by 2. That's a 28. Look, that's what it was when we totaled it. If it's true for some integer k, then it's true when n equals k plus 1. So if k is a 7, k plus 1 would be the 8, wouldn't it? So this is what we're going to get. I've got it written with the k here, and I've got it written with the 7 here to clarify it, all right? So we would have the quotient of k times k plus 1 and 2, which would be 7 times 7 plus 1 and 2, right? That's how we got the 56 divided by 2, the 28, all right? So we know that this is 28, right? The very next one would be the 7 plus 1, wouldn't it? So there would be an 8. That means this is this, okay? With the 7 in it, we would be doing 2 times 8, which is 16 divided by 2, which is an 8. So it's just another way of saying 8, isn't it? This, we get to this, with the 7s in it. That means we have 7 times 8 is 56, plus 2 times 8 is 16 divided by 2. This becomes this. With the 7s in it, we have an 8 times a 9 divided by 2. See that? Do you see what's happening? If I put the 7 in place of the k, does it make sense? That means we have 8 times 7 plus 1 plus 1 would be a 9. 8 times 9 is 72. We divide it by 2, we get a 36. And that is what happens when we add the 8th one, the number 8 for the next day. But what if we were trying to do this and figure out how much Bob gave me after 1,431 days? We would be able to use this to find it. Instead of adding all those numbers, we could just use this principle of mathematical induction, okay? So by Sunday, I'd have $28, and by the 8th day, I'd have $36, see? So remember the steps. We show that n is equal to 1 is true. Then we show for any positive integer k that p sub k is true, that middle number, okay, like our 7. And if that's true, if our 7 works out and it's true, then that means if we add 1 to it, so that would be the 8, wouldn't it? P sub k plus 1 would be the 8, must be true, all right? So that would be the 7 and the 8 when we were doing it with the 7 in it. Does that make sense? So I hope if you stuck with me through all this, you now can see how it makes sense. Because you could do this on your own by just adding them, right? When there's not that many numbers. This is great when there's a lot of numbers. If he did this every day for 2 years and 7 months, what money would I have? Well, you could figure out how many days are in 2 years and 7 months and then use this, right? And the last thing is what little x is saying. The principle of mathematical induction is the only property of numbers that guarantees that there's an infinite number of numbers, okay? Our next lesson is going to be the last one for Chapter 14. We're going to combine strategies. It's lesson 14.6. We're going to solve non-routine problems using a combination of strategies. I know this was a lot of information. Boy, my hand got sore writing this all out. It took me a while to plan this board. Look at all of this. So I hope you're having a great day. I hope this helped you in some way. If you're really lost and confused, maybe you could try watching it again or going back and learning about the series and stuff like that that you might have missed. And I'll see you next time. Bye.